Hello, everyone. This is first lecture of the second lecture of week 2, and today we're going to talk about the basic mathematics of probability. We've talked a little bit about set theory. Basically, mathematics of probability is based on set theory, and we make use of 3 fundamental assumptions to start us off. First of all, we assume that all probabilities are non-negative. So that should be actually greater than or equal to 0. And the probability of a certain event is 1. So basically this means that all our probabilities are going to be between 0 and 1. Lots of people express probabilities as percentages. I probably would discourage you not to, because when we're computing probabilities of intersection, we multiply probabilities, and you can't multiply percentages. You have to multiply the fractions between 0 and 1. So usually I express my probabilities as numbers between 0 and 1. So probability of the certain event is 1. That means the probability of the sample space, that's any outcome in the set of possible outcomes, must be equal to 1. So one of those outcomes must take place. If a sequence of events A1, A2, and so on and so forth are disjoint, so mutually exclusive, if one occurs, the other cannot occur, then the probability of their union is equal just to the sum of their probabilities. And we can see that to some extent. If A1 and A2 are disjoint, then the probability that I get into A1 or A2 is just going to be the sum of their areas. You think of this again as the outcome. I throw my dart. Where it lands is a possible outcome of the experiment. The area A1 plus A2, the bigger that area is, the bigger the probability of getting into one of those two areas. So there's a whole pile of important results that come out of this, but basically if you remember these 3 rules, you can just derive the entire rest of the probability theory. Fortunately, a lot of it's been done for us already, so we don't have to re-derive it every single time. So one important result is that the probability of the impossible event is equal to 0. As I mentioned, if a sequence of A's are disjoint, then the probability of their union is just the sum of their probabilities. Here I've specialized it. If we just have 2 events, A1 and A2, and they're disjoint, then the probability of their union is probability of A1 plus probability of A2. But I would suggest you don't remember this one. There's a more general formula that we'll develop shortly. Probability of A union A complement is, remember, A union A complement is just equal to the sample space. So everything in A or everything outside of A is the sample space, and this must be equal to 1. Also, A is disjoint from A complement, so probability of A union A complement is equal to the probability of A plus the probability of A complement. And that basically tells us the probability of A complement is 1 minus the probability of A. And we all know this intuitively. Probability of failure is 1 minus the probability of success. As I mentioned, the fact that probabilities are non-negative and that the certain event is probability 1 means that all probabilities must lie between 0 and 1. This one comes about but because of this idea of areas. If A is a subset of B, then A has smaller area than B, and it's inside B. And therefore, probability of A is less than or equal to the probability of B. Now, here's the more general rule that we're going to make use of. For any 2 events A and B, and I've shown a possibility over here that may overlap, the probability of A union B is the probability of A, which is this whole area here, plus the probability of B, which is this whole area here. The problem is that we have now added in. Here, let me just show this. So the probability of A is this area. And the probability of B is this area. And the problem is that if I add the area of A and the area of B together, then I'm adding the middle part twice. So you see both green lines and red lines in there. And we have to then subtract that once to get the area inside A or B. So the general rule is probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. So the probability of a union of two events leads to three terms on the right-hand side. And we'll see that this leads to trouble shortly. Yeah, okay, so we're going to look at what about the probability of a union of three events. So let's consider A, B, and C. The probability of their union, we could first of all add in A, the probability of A plus the probability of B plus the probability of C. But I see now I've added this intersection twice, this intersection twice, this intersection twice, and this intersection twice. And this triplet I've added in three times. So first thing I'm going to do is subtract this intersection, this intersection. That's the minus probability of A union and intersection B. Then I'm going to subtract this intersection, A intersection B, and I subtract B intersection C. Okay, so that gets rid of those things, but I'll see now I've actually subtracted the middle part three times. I added it in three times, and now I've subtracted three times. So I've left the middle part out at this point, so I've got to add it back in. So plus A intersection B intersection C gives me the area inside A or B or C. But we see what's happening here when we have a union of three events. We end up with 1, 2, 3, 4, 5, 6, 7 terms. Union of four events leads to 15 terms. So basically unions lead to piles of terms on the right-hand side. And so for unions, we really like it if the events are disjoint, because if the events are disjoint, then all of these intersection terms are zero. They are the probability of the null event. And in fact, then probability of the union of four things just becomes the sum of the four probabilities. So whenever I see a union, that's the first thing I ask, are those things disjoint? And if they are disjoint, I could just add up the individual probabilities, and I'm all set. Okay, so let's look at an example. Let's suppose we have 5 resistors connected in series, and the circuit is gradually, the voltage or the current on the circuit is gradually turned up until one of the resistors burns out. Suppose the probability that a given resistor will be the first to fail is proportional to its resistance, since P is equal to I squared R. So the higher the resistance, the more power it consumes. And the resistance, let's suppose, are 1, 2, 3, 4, and 5 ohms respectively. Let's determine the probability that the resistor which burns out first has resistance R less than or equal to 3 ohms. So here's our picture. We've got 5 resistors in series. First one has a 1 ohm, 2 ohms, 3 ohms, 4 ohms, 5 ohms. They don't actually have to be arranged that way. The answer will be the same no matter how you arrange them. Okay, so whenever I have these sorts of questions, I find that the best thing to do initially is clearly define your events. Clearly defined events is 95% of the problem, because once you've done that, the rest of it is just making use of formula that are in your summary pages, and then it's just plug in the numbers. So this is the hard step, just figuring out what these events should be, how they should be defined. By the way, I mentioned summary pages. You should look online. There's a set of summary pages. I think it's about 14 pages of all formulas and tables and stuff that I can't remember, which is most of it. And that stuff it's a nice, concise way of seeing all that information. You should get used to that those summary pages when you're working on your assignments, because it's a very quick way of finding the appropriate formula and probabilities and things like that. Okay, so we've defined our events. Fi is the event that the ith resistor burns out first. Our sample space then is F1, F2, F3, F4, F5. Then basically, if F1 occurs, it means that the first resistor burned out first. And if F4 occurs, it means the fourth resistor having resistance 4 ohms was the first to burn out. And the question then, I've got a sequence of events. Are these things a disjoint? Well, if resistor 1 is the first to burn out, it can't have been resistor 2 was the first to burn out, so these are disjoint. We define our event of interest. This is the event that R is less than or equal to 3 ohms. So that corresponds to the first resistor having 1 ohm, or the second resistor having 2 ohms, or the third resistor having 3 ohms is the first to burn out. Note that this was less than or equal to 3, so we included R3, or the event F3 in our event of interest. So the probability of A then is the probability of F1 occurring, or F2, or F3. As we mentioned, these are disjoint, so it's just equal to the probability of F1 plus F2 plus F3. And I don't have to worry about subtracting or adding in any of those intersections. The next challenge is to figure out what these probabilities are. Probability of F1, F2, and F3. So we have to assign probabilities to each possible outcome. Now we're told here that the probability that the resistor will be first to fail is proportional to its resistance. So if I go down here, I know probably that Fi fails is proportional to I, since the ith resistor has resistance I. In other words, we can write probability of Fi is equal to some constant times the resistance I. We also know that probably that one of these things burns out first, which is we're going to keep cranking up the current until something burns out. The probability that one of them fails must be 1. So probably the sample space is the probability of F1 or F2 or F3 or F4 or F5 taking place. Again, are these disjoint? Yes, they are disjoint. If one of them takes place, the others cannot. So it's just the sum of the probabilities, and that whole thing must add up to 1. Well, we know that's proportional to 1. This one is proportional to 2 ohms, proportional to 3 ohms, 4 ohms, 5 ohms. So this sum becomes C times 1 plus 2 plus 3 plus 4 plus 5, which is C times 15, and therefore C is 1/15. Once we have C, we can go back up and evaluate this probability that we're interested in. So probability of A is C times 1 plus C times 2 plus C times 3, which is 1/15 times 1 plus 2 plus 3, 6/15, or 0.4. Another example that we can look at, a bin contains 60 network cards, of which 5 are defective. Of course, you might wonder, if we know that 5 are defective, why didn't we just throw them out? But let's just, for illustration's sake, assume that we know 5 are defective, but we don't know which 5. If 2 network cards are chosen at random, what is the probability that none will be defective? Well, this problem, we've got a bin that is composed of 2 groups. There are 5 defective cards, and there are 55 non-defective cards, and we're going to select 2 network cards at random, and then looking for the probability that none of them are defective. Well, in order for none of them to be defective, the 2 network cards had to be selected from the 55 non-defective cards. But that's just the number of ways of selecting non-defective cards. We know that the total number of ways of selecting 2 cards from the 60 is just going to be, if we don't care about order, is going to be 60 choose 2. So to get no effectives, we must choose both cards from the non-defectives and 0 cards from the defective group. So we can do this in n equals 55 choose 2 and 5 choose 0. Well, 5 choose 0 is just 1, and this is 55 times 54 divided by 2 ways of selecting the 2 cards from the non-defectives. So our probability is obtained by dividing this number of ways of selecting non-defective cards by the total number of ways of selecting the 2 cards. So I got 55 choose 2 over times 5 choose 0 divided by the total number of ways of choosing 2 cards from the 60, and I end up with 99 over 118. Well, we can extend this problem a little bit. We've got the same bin, 60 cards, 5 are defective. We're still selecting 2 network cards. What is the probability that at least 1 will be defective? Well, there's actually 2 ways we can do that. Well, we know that this is the probability of none defective, and at least 1 is that either 1 is defective or 2 is defective, which is the complement of none defective. So we know the probability of at least 1 defective is 1 minus 99 over 118. Another approach to this problem is to just look at the number of ways of selecting at least 1 defective from the 2 groups. So we can start by selecting one defective card from the 5 defectives and 1 from the 55 non-defective, and then 2 defectives from the 5 defective and 0 from the non-defective, and that leads to this solution here. At least one it means that we select one from the non-defective, one from the defectives, and the number of ways of doing that is 55 choose 1 times 5 choose 1. And if we divide by the total number of ways of choosing 2 cards from 60, there's the probability that we get 1 defective. Then we add to that the probability of getting 2 defectives, and in order to get 2 defectives we have to choose 2 cards from the 5 defectives and 0 from the 55 non-defectives, and divide by the total number of ways of choosing 2 cards from 60. Add these two probabilities, we get 19 over 118. And as I mentioned, the other approach is to take probability of at least 1 is 1 minus the probability of none, which we saw the probability of none up here is 99 over 118, so 1 minus 99 over 118 is 19 over 118, as we had right here. Well, another example is to consider 2 identical pumps, A and B, in a pumping system. If one of the pumps fail, the system will still operate. So this is a redundant system. If the second pump is provided for reliability. Because of the added strain, however, the remaining pump is now more likely to fail than was originally the case if one of the other pump has failed. And suppose we're given the following information: if at least one pump fails by the end of the pump design life in 7% of all systems, and both pumps fail during that period on only 1% of all systems, what is the probability that pump A will fail during the pump design life? Well, as I mentioned, the main challenge with these problems is to clearly define your events. Once we have those, we can pretty much plug in the numbers. So I'm going to define event FA to be the event that pump A fails, and FB to be the event that pump B fails. So given that, after I've defined the events, the next thing I do is try to express the given information in terms of the events that I've defined. And if I can do that, as well as the question in terms of the events I've defined, then I know I've got a good set of defined events. If I can't express the information or the question in terms of my defined events, I've got to go back to my defined events. And by the way, you should keep your events as simple as possible. So for example, you would not have a single event for both pumps fail, because that's FA intersection FB. As soon as you see that intersection, you know you have a rule for computing probabilities. So keep the events simple, one thing at a time. Okay, so given these event definitions, we are told at least one pump fails by the end of the pump design life in 7% of all systems. That means the probability of FA or FB, so this is the union, that's the at least one, is 0.07. So I've converted from 7% to a fraction between 0 and 1. And we're also told that in the design life, the probability that both pumps fail is 1%. So probability of FA and FB is 1%. And this is what we're trying to avoid, that both pumps fail, because if that happens, our pumping system has failed. We're also told that these are identical pumps, so I assume from that that the probability of failure of one pump is exactly the same as probability of failure of the other pump, everything else being the same. So we're looking for probability of FA, probability that pump A will fail during the pump design life. And I would say the first thing you want to do, the next thing you want to do is draw a Venn diagram with labeled probabilities. Now, labeling the probabilities in a Venn diagram depends on a rule. Each area, disjoint area in a Venn diagram has to be labeled with its own probability. So for example, you would not label FA, the whole of FA here, with that probability. You have to start in the middle, and we know that the probability of the intersection is 0.01. We know that the sum of these two is 0.07. So the three numbers that go in here have to add up to 0.07. If these are identical, these two numbers have to be the same. So that means that this has to be 0.03, this has to be 0.01, this has to be 0.03. And these numbers, the 0.03 corresponds to this area where FA only happens. So everything outside of the intersection inside of FA. And this one is that area outside of the intersection as well. So that's the way you label Venn diagrams. Each disjoint area, so this area here, has its own probability. And the sum of those probabilities gives us the probability of that whole event. So we can see instantly from this Venn diagram that the probability of FA is going to be this area plus this area. 0.03 plus 0.04. Okay, another example. Let's suppose that 15% of all cars tested emit excessive hydrocarbons, 12% emit excessive carbon monoxide, and 8% emit excessive amounts of both. And then basically if a car is selected at random, we ask various questions related to the probability that emissions are exceeded. So I would start this again by defining events. Let's let H be the event that the car's hydrocarbon emissions are excessive. And usually I let the H or the event letter have something to do with the event that's taking place. So H for hydrocarbon. Not sure why I used M for carbon monoxide. I think I used M because C... No, I don't know why. Anyhow, carbon monoxide, probably because the monoxide is worse. So I let M be the event that a car's carbon monoxide emissions are excessive. M for monoxide because it's worse. It's the worst part of carbon. From these two events we are given, probability of H is excessive hydrocarbons is 15%, so the probability of H is 0.15. Probability of carbon monoxide is 12%, so that's 0.12. And we're told that the probability of both is 0.08. So I think the next thing we do is construct a properly labeled Venn diagram. And like I said, we start in the middle. So we start with the intersection and work our way out. So the 0.08 goes here. We know that all of probability of H is 0.15, so this area here must be 0.07. Same, we know that the probability of M is altogether 0.12, so this area has to be 0.04, so that these two add up to 0.12. And now we can just answer, from this Venn diagram, we could quickly answer the various questions. So the first question is, what is the probability that emissions of both hydrocarbon and carbon monoxide are excessive? So this is probability of H intersection M. We already know that. That's part of the given information, 0.08. Part B, what is the probability at least one test level is too high? So this is H or M. So H occurs or M or both. That's at least one. So that we get from here, we add up this plus this plus this. So 0.7 plus 0.08 plus 0.04 is 0.19. Part C is what is the probability that neither emission is too high. So this is going to be H union M complement, H union M complement, or H complement intersection M complement. Well, we can automatically see if we go through this, we're looking for the probability, here it is, H complement intersection M complement, that's everything outside of H or M. Well, we add up these three things, we know we got 0.19, that means outside has to be 0.81, so we can get that directly from our Venn diagram as 0.81. By the way, when you label this Venn diagram, you should also always label outside of the events that are shown. Then the whole thing is defined. You've got the area outside, area of H alone, H and M alone. And these four numbers should add up to 1. Then what's part D is what is the probability that hydrocarbon emission is not excessive? So this is H complement. That's everything outside of H, which is going to be 0.81 plus 0.04. Which gives me 0.85, or another way of putting this is 1 minus probability of H. We know probability of H is 0.15, so 0.85, we get this in two different ways. And the last one is what is the probability that only hydrocarbon emission is excessive. So we're looking for this region here where only in H, and that we know is 0.07. But by the way, in a test situation, I want you to show, or in its assignment for that matter, what the event is that you're computing here. So I want to see that you know that only H means H intersection with M complement. Okay, and that concludes this lecture. See you next time.